We have to do a little bit of chemistry to understand biology because, of course, cells are made of molecules, which are made of atoms. If you've taken chemistry recently, hopefully this will be really, really easy, basic stuff for you. So when we think about matter, anything that takes up space and has mass, what it's made up of are elements, pure substances that cannot be broken down by chemical reactions. And when you have two or more elements in a fixed ratio, that makes a compound, and when they share bonds, those are molecules. So the elements are what we have in the periodic table of the elements, of course. And so we're going to zoom in and think about what makes up each of these elements. So the elements have different chemical properties by themselves than they do when they're in a compound. So for example, sodium is an explosive solid when it's mixed with water, and I'm just going to show you a quick video of that.
Oh, this will be a good one. Oh, that's sodium, dude. That's a little bit of sodium.
And chlorine by itself is a toxic gas, but when they combine together, it makes sodium chloride, which we use to season our food all the time. When we think about what makes up the individual atoms of each element, we have three different subatomic particles that we need to think about. So an atom is a single piece of that particular element. It's the smallest unit of matter that still has the same chemical properties as that particular atom has. So within the particular atom, we have the nucleus. Now the nucleus of the atom is not the same as the nucleus of a cell, of course. Okay. Within the nucleus, we have positively charged subatomic particles called protons, and we have non-charged neutral particles called neutrons. And it's the number of protons that tells us which atom this is. Now, typically, the number of protons is balanced by negatively charged particles called electrons. And typically, these electrons are represented as falling in these neat little rings or shells around the nucleus of the atom. So you can see here that hydrogen normally has 1 proton and 1 electron. Carbon has 6 protons and 6 electrons, and also 6 neutrons. So I want you guys to pause the video here for a second and think of the elements that you know of. Which ones are going to be absolutely essential for biology? So go ahead and pause the video and think of a couple right now. So the elements that are found in all living organisms are oxygen, carbon, hydrogen, nitrogen, phosphorus, and sulfur. You might have guessed a couple other things in your list, and a lot of those are essential for our biology, but they're not necessarily essential for every single organism. So you're mostly made of water, you're mostly made of oxygen and hydrogen, and by dry mass, you're mostly made of carbon and nitrogen. When we look at the periodic table, there's a couple of pieces of information about each of the elements that are shown. So the atomic number is a smaller number, and the atomic number tells us the number of protons in that particular element. So for carbon, it's atomic number 6, which means there's 6 protons. There are also 6 neutrons for most kinds of carbon. And so the atomic mass is the sum of the protons and the neutrons. But if you look at a periodic table, you'll notice that the atomic mass is usually a decimal number. So the atomic mass shows us that there's not exactly 6 protons and 6 neutrons. On average, there's 6 protons and 6 neutrons, but there's actually some isotopes of carbon that have extra neutrons. An isotope is that particular element, but it has a differing number of neutrons. So for example, carbon-14 has 6 protons, but it has 8 neutrons, and so it has an atomic mass of 14. Carbon-14 is rare, and so it only shifts the atomic mass up a little bit. This is the average mass of a carbon atom. On the other hand, if you change the number of electrons for a particular element, that creates an ion. So an ion has a differing number of electrons compared to protons. The number of protons tells us which element it is, but it's the electrons that are going to determine how a particular element behaves chemically. Especially the valence electrons are the ones that are going to determine how a particular element reacts. So if we look at oxygen, for example, oxygen is atomic number 8 and has an atomic mass of around 16. So what that means is oxygen has 8 protons and it also has 8 electrons. Those electrons fall into these shells. And the way that the electrons fall, there tends to be 2 electrons in the very inner shell, and then the next shell has room for up to 8 electrons. And if we had a larger element, we could have 8 more electrons in the next shell out. But oxygen only has 8 electrons altogether, and they're going to fall in a particular pattern. So the first 2 electrons will pair up with each other in that inner shell. And the next shell out, the electrons tend to fall in a particular pattern. So the pattern for electrons is the first 2 pair up, and then the next one, 3, 4, and 5 spread out. And then if there's more than that, 6, 7, and 8 will pair up with the ones that were there before. So for oxygen, since it has 8 electrons total, 2 in the first shell, it has 6 in the outer shell. The first 2 end up here, then 3, 4, 5, and then 6 falls over here. But this outer shell, this valence shell, has room for up to 8 electrons. That means there are 2 empty spots, and it's those empty spots where oxygen can form bonds with other elements. Those 2 empty spots on our oxygen could be a place where hydrogen could form a covalent bond. Hydrogen is atomic number 1. It has 1 proton. It also has 1 electron, and that 1 electron from hydrogen can be shared with oxygen to fill in that empty gap. And over here, another hydrogen could fill in that gap and form a water molecule. In your textbook, you can see molecules represented in different ways. You might see the name or the molecular formula for a particular compound or molecule. You could see an electron distribution diagram like I've been drawing. Those pairs of electrons can be represented by pairs of dots, or a pair of electrons is more often represented as a straight line that represents a covalent bond. But in biology, more often than not, you'll see these space-filling models that show the overall shape of the molecule. So these electron distribution diagrams are one way of modeling and representing what the electrons do, but it's not really a precise picture. Those 2 electrons in the inner shell tend to fall in this sphere where they could be anywhere in this cloud. And these pairs of electrons in the second shell fall in these lobules called orbitals. And so instead of a flat molecule, we really get 3-dimensionally shaped molecules, which is the whole subject of organic chemistry. The shape of the molecule actually determines how it functions, and this is true for things as simple as water or methane, and things more complex such as hormones and the receptors that they interact with. If you have a piece of a molecule that has a particular shape that matches the shape of a receptor, if you can make another molecule that mimics its shape, it can mimic its function. So atoms want to fill their valence shell. They want to fill it up with electrons. And there's a couple different ways that this could be accomplished. They could either share, like we saw with our water molecule, or they could give their electrons away, or they could steal electrons from other atoms. And these are the different kinds of bonds. An ionic bond is the situation where electrons are transferred. One atom gives away its electrons and the other gains electrons. So sodium, for example, has just one electron in its outer or valence shell. And chlorine has 7 electrons in its valence shell and only one empty spot. Chlorine is also highly electronegative. It loves electrons and can pull them towards itself. So sodium can give away its one valence electron, and now the next shell in is totally full and it's satisfied. And chlorine can steal that one electron from sodium, and now its valence shell is full and it's satisfied. But when this happens, sodium is now missing an electron. It has one more proton than electrons, and so it has a +1 charge. It's a sodium ion. And chlorine now has one more electron than it has protons, and so it has a -1 charge. It's a chloride ion. Electrons can also be shared between atoms. So like we saw with the water molecule that I drew, electron from hydrogen can be shared in that empty spot with oxygen, and another hydrogen can share another electron with it. The sharing of electrons can be fair and equal, or it can be unequal. Elements or atoms of the same type are going to share electrons fairly with each other. So if you have 2 carbons sharing electrons, they'll share fairly. Or if you have 2 oxygens sharing with each other. Or if you have elements like carbon and hydrogen, they tend to share equally. But other elements are highly electronegative. They love electrons and they pull them towards themselves. Now, the general trend in the periodic table is as you go up and to the right, those elements tend to be more electronegative. But the most important one for biology is oxygen. Oxygen is very electronegative. It steals electrons. It pulls electrons to itself. So in our water molecule, the electrons actually get pulled towards the oxygen side. And what that means is that the oxygen side is partially negative. This is supposed to be a delta symbol, which means a partial charge on this side. And the hydrogens are kind of losing the tug of war, and their electrons are getting pulled away from them. And so they're partially positive. So when the electrons are shared, but they're shared unequally, that's called a polar covalent bond. So just one more thing about covalent bonds. A pair of electrons being shared makes up a single bond. So if we redrew this water molecule, instead of showing the electron distribution diagram, we would have oxygen covalently bonded to hydrogen and to another hydrogen. And that straight line represents a pair of electrons being shared between them. But you can have more than one pair of electrons being shared. So instead of water, if we had 2 oxygens, each oxygen has 2 unpaired electrons that want a partner to fill the valence shell. And so you can share 2 pairs of electrons between 2 oxygen atoms, and that forms a double bond. Each bond is made of a pair of electrons. You can even have triple bonds where 3 pairs of electrons are being shared. Polar covalent bonds lead to the formation of polar molecules where one side is partially positive and the other side is partially negative. And when you have opposite partial charges can attract. So the negative side of one water molecule can actually be attracted to the positive side of another water molecule. And this partial charge attraction between 2 water molecules is called a hydrogen bond. It's called a hydrogen bond because usually hydrogens are wimpy at holding their electrons, and so they end up partially positive. And so it's the hydrogen side of many molecules that hydrogen bonds to other molecules or atoms, but it doesn't require that a hydrogen is part of it. One water molecule can actually form 4 different hydrogen bonds with 4 different water molecules. It seems like a simple concept, but I'm telling you right now, write this down. One water molecule is made of 2 polar covalent bonds. H2O is held together by polar covalent bonds. But different water molecules stick to each other through hydrogen bonds. Molecules that are polar mix well with water. They're hydrophilic, whereas non-polar molecules don't mix with water. They're hydrophobic.